Every man who has ever lived has felt the pull, but few have truly understood what holds them to this earth.
I spent the better part of my life believing, as most do, that objects simply fall because that is their nature. Heavy things drop, light things float. The moon circles overhead because God set it in motion. Simple truths that required no deeper questioning. But when I began to examine the mathematics behind these everyday occurrences, I discovered something that changed not just natural philosophy, but my understanding of how every single thing in creation connects to every other thing. What I found was not merely a force that makes apples fall from trees. I found the invisible hand that shapes the cosmos, governs the tides, determines the very structure of matter itself, and binds every star to its neighbor across the vast emptiness of space. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. A leather-bound notebook sits before me still, its pages yellowed with age, but the geometric proofs within as sharp as the day I first traced them with my quill. This Cambridge mathematics notebook taught me to see patterns where others saw only chaos, and without it, I would never have questioned why things fall. I was 23 when the Great Plague forced Cambridge to close its doors in 1665. Most of my fellow scholars saw this as a catastrophe, an interruption of proper learning. I saw it as liberation. For the first time in my adult life, I was free from the endless recitations of Aristotle's natural philosophy, free from professors who demanded we accept that heavy objects fall faster than light ones simply because the ancients said so. At Woolsthorpe Manor, my mother's modest estate in Lincolnshire, I found myself with nothing but time and questions. The orchard behind the house became my laboratory, though I did not know to call it that then. I would sit beneath the apple trees with my notebook, watching the fruit drop as autumn progressed. Every apple fell straight down, every one. Never sideways, never upward, always toward the earth. The accepted wisdom of my time explained this simply enough. Heavy objects contained more of the element earth, and earth naturally sought its proper place at the center of the cosmos. It was a tidy explanation that had satisfied learned men for nearly 2,000 years. But watching those apples fall, I began to notice something that troubled this ancient certainty. I dropped objects of different weights from my bedroom window, a stone and a feather, a heavy book and a light coin. The feather drifted, yes, but when I placed both the stone and the book in identical containers to eliminate the air's interference, they struck the ground at precisely the same moment.
How could this be?
If heavy objects truly fell faster than light ones, my Cambridge notebook contained the tools to examine this puzzle. Geometry showed me how to measure angles and calculate ratios. Arithmetic revealed relationships between numbers that mirrored relationships in nature. Most importantly, algebra taught me that unknown quantities could be discovered through logical manipulation of known relationships. I began timing the fall of objects from different heights using my pulse as a crude timepiece. The pattern that emerged contradicted everything I had been taught. Objects did not fall at speeds proportional to their weight. Instead, they fell at speeds that increased in proportion to time, regardless of their mass. A stone dropped from twice the height did not take twice as long to fall. It took approximately 1.4 times as long, the square root of 2. This discovery might have remained a curious observation, filed away with other natural oddities. But something deeper was stirring in my mind. If the speed of falling objects followed mathematical rules, what other natural phenomena might yield to mathematical analysis? I began studying the work of Galileo Galilei, whose observations of the heavens had caused such controversy in my father's generation. Galileo had described the moons of Jupiter, celestial bodies that clearly orbited something other than Earth. He had observed the phases of Venus, proving that planet traveled around the sun. Most relevant to my growing obsession, he had studied the motion of projectiles and discovered that they followed curved paths called parabolas. But Galileo had stopped short of asking why objects moved as they did. He described motion but did not attempt to explain what caused it. That question consumed me through the long winter months at Woolsthorpe. I carried my notebook everywhere, sketching the paths of thrown stones, calculating the arcs of projectiles, measuring the time it took for objects to fall from various heights. Each measurement confirmed the same troubling truth. Motion followed mathematical laws with the same precision as geometric theorems. During those plague years, I also began my study of optics, fascinated by the way sunlight separated into colors when passed through a prism. Here, too, mathematics revealed hidden order. The angles at which light bent followed precise relationships. Color itself seemed to emerge from mathematical properties of light that no one had previously suspected. But it was the falling objects that haunted me most persistently. Each apple that dropped, each stone that fell, challenged me to find the cause behind the mathematical pattern. Weight alone could not explain why things fell. Position could not explain it either, since objects fell regardless of where they were dropped. Time seemed irrelevant, since the pattern of acceleration remained constant whether I dropped objects in morning or evening. Force could act on all objects equally, regardless of their composition, size, or position. What power could reach out invisibly to pull things toward the Earth with such mathematical precision? My notebook filled with calculations exploring these questions. I drew diagrams showing how the speed of falling objects increased over time. I created tables comparing the fall rates of different materials. I sketched geometric relationships between distance, time, and acceleration. Each page brought me closer to a truth I could not yet name. The scholars at Cambridge, when they returned after the plague, were not particularly interested in my rustic observations. Natural philosophy in those days concerned itself with grand theories about the nature of matter and the structure of the cosmos. Questions about why apples fall seemed trivial beneath the dignity of serious intellectual pursuit. But I had learned something during those months of solitude that would guide the rest of my life's work. Mathematics was not merely a tool for abstract reasoning or commercial calculation. Mathematics was the language in which nature itself was written. Every falling object spoke in equations. Every projectile traced mathematical curves through the air. Every natural phenomenon, however humble, contained geometric relationships waiting to be discovered. The notebook I filled during those plague years became the foundation for everything that followed. Its pages contained the first glimmers of understanding that would eventually revolutionize how we comprehend the workings of the world. But at the time, sitting in my mother's orchard with my quill and inkwell, I knew only that the universe was far more mathematically ordered than anyone had previously imagined. And I suspected, though I could not yet prove, that the same force responsible for pulling apples toward the Earth might be responsible for holding the entire cosmos together. Kepler's Astronomia Nova arrived at my study in 1666, its pages dense with astronomical observations and mathematical analysis that would transform my understanding forever. I can still see my marginal notes scrawled across those worn pages, marking the moments when celestial mechanics revealed its hidden harmony to my searching mind. Johannes Kepler had spent decades studying the orbit of Mars, wrestling with observations that refused to fit the ancient assumption of perfect circular motion. What he discovered challenged 2 millennia of astronomical tradition. Planets moved in ellipses, not circles. They traveled faster when closer to the sun, slower when farther away. Most remarkably, the time required for a planet to complete its orbit related mathematically to its distance from the sun, following what would become known as Kepler's third law. But Kepler had described these relationships without explaining what caused them. He had mapped the choreography of the heavens without identifying the choreographer. That missing piece haunted me as I studied his work by candlelight in my Woolsthorpe study. Galileo's observations added another layer to the puzzle. His primitive telescope had revealed 4 moons circling Jupiter, proving that not everything in the heavens revolved around Earth. These Jovian satellites followed their own complex dance, sometimes visible, sometimes hidden behind their parent planet, always returning to their appointed positions with clockwork precision. The implications troubled the established order of natural philosophy if moons could orbit Jupiter while Jupiter itself orbited the sun. And if these celestial bodies followed mathematical laws rather than divine caprice, then perhaps the heavens and the earth operated according to the same fundamental principles. This possibility fascinated me beyond measure. During my Cambridge years, I had been taught to regard celestial and terrestrial motion as entirely different phenomena. Objects on Earth fell toward the center because they contained the element Earth, which naturally sought its proper place. Celestial bodies moved in eternal circles because they were composed of quintessence, a perfect substance that naturally moved in perfect geometric forms. What if this ancient distinction was simply wrong? What if the force that pulled apples toward the ground also guided the moon in its orbit around Earth? The idea seemed preposterous at first consideration. How could the same power that operated within a few feet of Earth's surface reach across the vast emptiness of space to influence celestial bodies? Yet the mathematical patterns suggested an underlying unity that could not be ignored. I began calculating the moon's orbital motion using the same principles I had applied to falling objects. If the moon was indeed falling toward Earth but moving so quickly sideways that it continuously missed our planet, then its centripetal acceleration should follow the same mathematical relationship as objects dropped from my window. The numbers proved revelatory. The moon orbits Earth at a distance of approximately 60 Earth radii, taking 27 days to complete its circuit. Using Kepler's observations and geometric analysis, I calculated that the moon's acceleration toward Earth was approximately 1/3600th the acceleration of objects falling at Earth's surface. 60 squared equals 3,600. The relationship was exact, within the limits of my calculations and the astronomical observations available at the time. This could not be coincidence. The same force that governed falling apples also governed the moon's orbit, but its strength diminished with the square of the distance. If I doubled the distance from Earth's center, the gravitational force became 1/4 as strong. If I tripled the distance, the force became 1/9 as strong. The mathematical relationship suggested something even more remarkable. If gravitational attraction followed an inverse square law, then this same principle should govern the orbits of all the planets around the Sun, and indeed all celestial motions throughout the cosmos. I tested this hypothesis against Kepler's observations of planetary motion. Mars, with its well-documented elliptical orbit, provided an excellent test case. If the Sun's gravitational attraction followed an inverse square law, and if this attraction provided the centripetal force keeping planets in their orbits, then Kepler's laws should emerge naturally from the mathematics. The calculations consumed weeks of intense work. I had to develop new mathematical techniques to handle the complexity of elliptical orbits and varying speeds, but gradually the pieces fell into place. Kepler's first law, describing elliptical orbits, followed inevitably from inverse square attraction toward a fixed center. His second law, describing how planets sweep out equal areas in equal times, emerged from the conservation of angular momentum under central force attraction. His third law, relating orbital periods distances, arose directly from the inverse square relationship. Every astronomical observation confirmed the same startling conclusion. The force that made objects fall on Earth was the same force that kept planets in their orbits around the Sun, moons in their orbits around planets, and presumably all celestial bodies in their appointed courses throughout the universe. This realization carried profound implications that extended far beyond astronomy. If a single mathematical law could describe both terrestrial and celestial motion, then the universe possessed a fundamental unity that previous natural philosophy had never suspected.
The distinction between earthly and heavenly phenomena,
which had formed the cornerstone of Western thought since Aristotle, was simply an artifact of limited observation and mathematical ignorance. My correspondence with members of the Royal Society began to reflect these revolutionary ideas, though I presented them cautiously. Robert Hooke had already speculated about inverse square relationships in gravitational attraction, but he lacked the mathematical tools to develop these insights into a comprehensive theory. Edmund Halley visited me at Cambridge specifically to discuss orbital mechanics and left convinced that I had discovered something of extraordinary importance. Yet I encountered significant resistance from colleagues who could not accept that invisible forces might act across empty space. The mechanical philosophy of René Descartes dominated natural philosophy in those days, insisting that all physical effects required direct contact between material substances. Descartes proposed that planets were carried around the Sun by vast whirlpools of subtle matter, a theory that preserved mechanical causation but failed to explain Kepler's precise mathematical relationships. My gravitational theory demanded that matter could somehow reach across empty space to influence other matter without any intervening mechanism. This seemed to violate fundamental principles of mechanical philosophy, returning physics to the occult influences that the scientific revolution had worked so hard to eliminate. But mathematics cared nothing for philosophical preferences. The inverse square law of gravitational attraction explained every celestial observation with unprecedented precision. It predicted the return of comets, the precession of planetary orbits, and the complex motion of the moon with accuracy that surpassed all previous astronomical theories. As I filled page after page with calculations confirming the universal nature of gravitational attraction, I began to understand that I had discovered something far more significant than an explanation for falling objects. I had found the fundamental organizing principle of the cosmos, the invisible architecture that held the universe together and governed its every motion from the smallest scale to the largest.
Sheets of parchment before me are covered with equations that changed everything, calculations proving that gravitational force weakens with the square of distance.
These inverse square calculations, scratched out in my careful hand during countless late nights, represent the moment when scattered observations crystallized into universal law. Developing the mathematical proof required techniques that simply did not exist when I began this work. I had to invent new methods of calculation, what I would later call the method of fluxions, to handle the continuously changing relationships between force, motion, and time. Each equation built upon the previous one, creating a logical structure that could support the weight of cosmic understanding. The fundamental insight emerged gradually through rigorous mathematical analysis. If every particle of matter attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, then all observed motions follow inevitably from this single principle. I tested this hypothesis against every astronomical observation available to me. The orbit of Mercury closest to the Sun and therefore most influenced by solar gravity matched my calculations precisely. Venus, Earth, and Mars all followed paths that my equations predicted with extraordinary accuracy. Most remarkably, Jupiter and Saturn, those distant giants whose movements had puzzled astronomers for centuries, obeyed the same mathematical relationships despite their vast distances from the Sun. But the real test came with cometary observations. These mysterious visitors to the inner solar system followed extremely elongated elliptical paths that brought them close to the Sun before flinging them back into the outer darkness. If gravitational attraction truly followed an inverse square law, then comets should behave like planets with extremely eccentric orbits, accelerating dramatically as they approached the Sun and slowing as they receded. Edmund Halley provided crucial assistance in these calculations. His meticulous observations of the Great Comet of 1682, combined with historical records of similar apparitions, allowed me to test my theory against objects that spent most of their time far beyond the realm of ordinary planetary observation. The mathematics worked perfectly. The same gravitational principles that govern planetary motion also explain the precise timing of cometary returns. My correspondence with the Royal Society during this period reflects both excitement and frustration. Robert Hooke had independently speculated about inverse square relationships and gravitational attraction, and he claimed priority for the fundamental insight. This led to an unfortunate dispute that clouded what should have been a period of pure scientific discovery. Hooke's qualitative understanding of inverse square attraction was correct, but he lacked the mathematical tools to develop this insight into a quantitative theory capable of making precise predictions. The difference between intuiting a relationship and proving it mathematically is the difference between guessing and knowing. My calculations provided the rigorous foundation that transformed speculation into science. The philosophical implications of universal gravitation troubled many of my contemporaries far more than the mathematical details. The idea that matter could somehow reach across empty space to influence other matter without any intervening mechanism seemed to violate the fundamental principles of mechanical philosophy that had guided natural science since the time of Descartes. René Descartes had insisted that all physical effects required direct contact between material substances. His system of vortices, vast whirlpools of subtle matter that supposedly carried planets around the Sun, preserved this mechanical principle but failed utterly to explain the precise mathematical relationships that Kepler had observed. My gravitational theory abandoned mechanical causation in favor of mathematical description, a shift that many scholars found deeply unsettling. I struggled with this philosophical problem myself. How could matter act where it was not present? What mechanism could transmit gravitational influence across the vast emptiness of interplanetary space? The mathematics demanded that such action at a distance exist, but I could provide no mechanical explanation for how it operated. In the end, I chose mathematical truth over philosophical comfort. Whatever the ultimate mechanism might be, gravitational attraction clearly followed precise mathematical laws that could be observed, measured, and predicted with extraordinary accuracy. The universe operated according to mathematical principles, whether or not we could explain why those principles existed. This decision to accept mathematical description without mechanical explanation marked a fundamental shift in natural philosophy. Instead of asking what gravity was in some essential sense, I focused on describing what gravity did in mathematical terms. This empirical approach would prove far more fruitful than centuries of speculation about the hidden essences of natural phenomena. The universality of gravitational attraction gradually became clear through systematic analysis. Every piece of matter in the universe, from the smallest grain of sand to the largest star, attracted every other piece of matter according to the same mathematical relationship. The force was always proportional to the product of the masses involved and always inversely proportional to the square of the distance between them. This meant that I, sitting in my study, exerted a gravitational pull on every star in the heavens, and every star pulled back with equal force. The effect was vanishingly small due to the enormous distances involved, but the mathematical relationship demanded that it exist. The universe was bound together by an infinite web of gravitational attractions, each following the same precise mathematical law. The implications for understanding the structure of the cosmos were staggering. If gravitational attraction truly was universal, then the same force that governed planetary motion also determined the behavior of double stars, the clustering of stellar systems, and the overall architecture of the heavens. The universe possessed a fundamental unity that extended from the smallest scale to the largest. My calculations also revealed why objects fall with the same acceleration regardless of their mass. The gravitational force on any object is proportional to its mass, but so is its resistance to acceleration. These two effects exactly cancel each other, ensuring that all objects fall at the same rate in the absence of air resistance. This seemingly paradoxical result follows inevitably from the mathematical structure of universal gravitation. The precision of gravitational calculations allowed for predictions that could be tested against future observations. I calculated that the orbit of the moon should precess slightly due to the sun's gravitational influence, and this prediction was subsequently confirmed by careful astronomical measurement. The return dates of comets could be predicted years in advance, as Halley demonstrated with the comet that now bears his name. Perhaps most remarkably, the mathematical theory predicted phenomena that had never been observed. The gravitational influence of Jupiter and Saturn on each other's orbits should produce small but detectable variations in their positions over time. These perturbations, invisible to casual observation but accessible to precise calculation, would later provide crucial tests of gravitational theory. By 1684, I had developed the mathematical framework of universal gravitation to the point where it could explain every known celestial phenomenon with unprecedented accuracy. The theory made precise predictions about future observations and revealed hidden connections between apparently unrelated natural phenomena. What had begun as a simple question about falling apples had evolved into a comprehensive understanding of the fundamental force that shaped the cosmos. But developing the theory was only half the battle. Convincing the scientific community to accept such a radical departure from established natural philosophy would require a comprehensive demonstration that left no room for doubt. The task ahead was to present these mathematical insights in a form that would compel acceptance even from the most skeptical observers.
Descartes' Principia.
Philosophia sits on my shelf even now, its pages filled with mechanical explanations that my discoveries rendered obsolete. I debated against this book countless times, its vortex theory representing everything that stood between the scientific community and acceptance of universal gravitation. The resistance I encountered was not mere scholarly disagreement, but a fundamental clash between two incompatible ways of understanding nature. René Descartes had constructed an elegant mechanical system that explained all natural phenomena through the interaction of matter and motion. According to his theory, the planets were carried around the sun by vast whirlpools of subtle matter, invisible vortices that filled all space and provided the mechanical contact necessary for motion. This system preserved the principle that matter could only influence other matter through direct physical contact, maintaining what seemed like philosophical respectability in natural science. My gravitational theory shattered this mechanical worldview by demanding that matter could somehow act across empty space without any intervening substance. To the Cartesian philosophers who dominated European universities, this seemed like a return to the occult qualities and hidden influences that the scientific revolution had worked so hard to eliminate. They accused me of abandoning rational natural philosophy in favor of mystical speculation. The attacks came from multiple directions. Gottfried Leibniz, perhaps the most brilliant philosopher of our age, argued that action at a distance violated the fundamental principle of sufficient reason. How could matter know to attract other matter at great distances? What determined the precise mathematical relationship of the inverse square law? Without answers to these questions, Leibniz insisted, gravitational theory remained an incomplete and philosophically unsatisfying hypothesis. Christian Huygens, whose work on pendular motion and planetary dynamics I greatly respected, rejected universal gravitation on similar grounds. He could accept that some unknown mechanism might cause gravitational effects, but he refused to believe that these effects could propagate instantaneously across vast distances with no material medium. The idea that the sun's gravitational influence reached Neptune immediately, despite the enormous space between them, struck him as physically impossible. The Cartesian establishment at Cambridge proved particularly resistant to my ideas. Dr. John Keel, who held the civilian chair of astronomy at Oxford, spent years promoting Descartes' vortex theory and attacking my mathematical approach to celestial mechanics. He argued that mathematics alone could never provide genuine understanding of natural phenomena, that true science required mechanical explanations that showed how effects were produced through the interaction of material substances. Even members of the Royal Society, who should have been most receptive to empirical evidence, struggled with the philosophical implications of universal gravitation. They could not deny the mathematical precision with which my theory explained astronomical observations, but they continued to hope that some mechanical explanation might eventually be found to account for gravitational phenomena without requiring action at a distance. The personal cost of promoting these revolutionary ideas was considerable. I found myself increasingly isolated from the mainstream of natural philosophy, regarded by many as either a mathematical genius who had lost his way philosophically, or a dangerous innovator who threatened the rational foundations of science. The controversy with Robert Hooke over priority in discovering inverse square attraction only deepened my sense of isolation and frustration. Hooke's claim to have discovered the fundamental principle of gravitational attraction before me was technically correct in a limited sense. He had indeed speculated that planetary motions might result from an attractive force that diminished with the square of distance. But speculation without mathematical proof is merely guesswork. Hooke lacked the mathematical tools to transform his insight into a quantitative theory capable of making precise predictions. The difference between Hooke's qualitative insight and my mathematical demonstration illustrates the broader conflict between old and new approaches to natural philosophy. The traditional method relied on reasonable speculation about the hidden mechanisms underlying natural phenomena. My approach focused on mathematical description of observable relationships, setting aside questions about ultimate mechanisms in favor of precise quantitative understanding. This methodological shift troubled many of my contemporaries far more than any specific theoretical claim. By abandoning the search for mechanical explanations and accepting mathematical description as sufficient, I seemed to be giving up on the goal of truly understanding nature in favor of merely describing it. Critics argued that this represented a retreat from genuine science into mathematical formalism. Yet I had strong allies who recognized the revolutionary power of mathematical natural philosophy. Edmund Halley provided crucial support during the most difficult period of developing gravitational theory. His encouragement and financial backing made it possible for me to complete the Principia, despite the hostility I encountered from other quarters. Halley understood that mathematical precision could provide a more reliable foundation for natural science than philosophical speculation about hidden mechanisms. David Gregory at Edinburgh and John Keel at Oxford, despite his initial Cartesian leanings, eventually became powerful advocates for gravitational theory. They recognized that the mathematical success of universal gravitation outweighed any philosophical discomfort it might cause. Their influence helped establish Newtonian natural philosophy in British universities, providing a foothold for the new mathematical approach to physics. The continental resistance proved more persistent and better organized. The French Academy of Sciences remained committed to Cartesian vortex theory well into the 18th century, refusing to accept that action at a distance could provide a legitimate foundation for natural science. German universities, influenced by Leibniz's philosophy, developed alternative theories that attempted to preserve mechanical causation while accounting for gravitational phenomena. I responded to this resistance not through philosophical argument, but through mathematical demonstration. Each new prediction confirmed by observation strengthened the case for universal gravitation and weakened alternative theories. The return of Halley's comet in 1758, exactly as predicted by gravitational calculations, provided particularly dramatic confirmation of my theory's power. Perhaps the most effective response to philosophical objections came from the theory's practical success. Navigators could use gravitational calculations to predict tidal patterns with unprecedented accuracy. Astronomers could calculate planetary positions years in advance. Engineers could design more effective pendulum clocks by accounting for variations in gravitational acceleration at different latitudes. These practical applications demonstrated that whatever philosophical problems gravitational theory might raise, it provided genuine knowledge that could be used to predict and control natural phenomena. Gradually, the weight of empirical evidence began to overcome philosophical resistance. Young scholars, less committed to established theoretical frameworks, found themselves drawn to the mathematical elegance and predictive power of gravitational theory. They were willing to accept action at a distance as a brute fact about nature rather than a philosophical problem requiring immediate solution. The generational change in natural philosophy proved crucial to the acceptance of universal gravitation. Older scholars who had built their careers on Cartesian mechanical principles found it difficult to abandon frameworks that had guided their thinking for decades. Younger scholars, approaching these questions without established commitments, could evaluate gravitational theory on its empirical merits rather than its philosophical acceptability. By the early 18th century, the tide of opinion had clearly turned in favor of gravitational theory, at least in Britain and its intellectual sphere of influence. Continental resistance persisted longer, but even there, the accumulation of successful predictions gradually eroded opposition to universal gravitation. Looking back on this period of intellectual struggle, I recognize that the resistance to my ideas was not simply obscurantism or professional jealousy. Cartesian mechanical philosophy represented a genuine attempt to understand nature through rational principles that preserved human comprehension of natural processes. My gravitational theory demanded that scientists accept mathematical relationships they could describe precisely but could not explain mechanically. This transition from mechanical explanation to mathematical description marked a fundamental transformation in natural philosophy. It established mathematics as the primary language of physical science and opened the door to theoretical frameworks that might violate common sense but could be tested against empirical observation. The universe, I had discovered, operated according to mathematical laws that human reason could discover but might never fully comprehend in mechanical terms.
The first edition of my Principia Mathematica rests in my study.
Its leather binding worn from years of consultation and revision. This book represents the culmination of 2 decades of mathematical investigation, geometric proofs demonstrating that the same force governing falling apples also guides the motion of planets, comets, and tides. When I completed this work in 1687, I knew I had created something that would fundamentally change how humanity understands its place in the cosmos. Writing the Principia required developing an entirely new form of mathematical exposition. I could not simply present my calculative methods, which many scholars would have found incomprehensible or controversial. Instead, I chose to present my discoveries using the rigorous geometric methods that had been respected since Euclid's time, translating my insights about motion and force into propositions that could be demonstrated with the same logical certainty as geometric theorems. Each proposition built systematically upon previous results, creating an unassailable logical structure that led inevitably to universal gravitation. I began with simple definitions of mass, motion, and force, establishing the conceptual foundation necessary for everything that followed. The 3 laws of motion emerged from careful analysis of how bodies interact, providing the fundamental principles governing all mechanical phenomena. The first law established that objects in motion continue moving in straight lines unless acted upon by external forces, while objects at rest remain at rest unless similarly compelled to move. This principle of inertia contradicted the Aristotelian notion that motion required continuous application of force, establishing instead that force was needed only to change motion, not to maintain it. The second law quantified the relationship between force, mass, and acceleration, showing that the change in motion was always proportional to the applied force and occurred in the direction of that force. This mathematical relationship provided the foundation for calculating how gravitational attraction would affect the motion of celestial bodies. The third law demonstrated that forces always occurred in pairs, with every action producing an equal and opposite reaction. This reciprocal principle meant that when Earth attracted an apple, the apple attracted Earth with equal force, though Earth's vastly greater mass made its response imperceptible. From these fundamental principles, I derived the mathematical relationships governing orbital motion, showing how Kepler's empirical laws emerged inevitably from gravitational attraction following an inverse square law. The geometric demonstrations were rigorous and comprehensive, leaving no room for doubt about the mathematical connections between terrestrial and celestial mechanics. But the true power of the Principia lay in its ability to explain phenomena that had puzzled natural philosophers for centuries. The complex motion of the moon, with its varying speed and slightly shifting orbital plane, followed precisely from the combined gravitational influences of Earth and Sun. I could calculate exactly how solar attraction perturbed the moon's orbit, accounting for observations that previous theories had been unable to explain. The tides presented another striking demonstration of gravitational theory's explanatory power. For millennia, natural philosophers had speculated about the connection between tidal patterns and lunar motion without developing any quantitative understanding of the relationship. My gravitational analysis revealed the mechanism with mathematical precision. The moon's gravitational attraction pulls more strongly on the side of Earth facing it than on Earth's center, and more strongly on Earth's center than on the side facing away. This differential attraction stretches Earth slightly along the line connecting our planet to the moon, creating 2 tidal bulges that follow the moon's position as Earth rotates. The sun's gravitational influence modifies this pattern, creating the complex cycle of spring and neap tides that mariners had observed for centuries without understanding. The mathematical accuracy of these tidal calculations astonished even my supporters. I could predict the timing and magnitude of high and low tides for any location, accounting for local geographical factors that modified the basic gravitational pattern. This practical application of gravitational theory provided powerful evidence that my mathematical approach captured genuine physical relationships rather than mere geometric abstractions. Cometary motion offered perhaps the most dramatic confirmation of universal gravitation. These mysterious visitors had been regarded as supernatural portents throughout human history, their unpredictable appearances and spectacular behavior seeming to defy natural explanation. My gravitational analysis revealed that comets were simply celestial bodies following extremely elongated elliptical orbits around the Sun. Edmund Halley provided crucial observational data for testing my cometary calculations. The Great Comet of 1682, which had appeared with spectacular brightness and an enormous tail, could be traced through historical records to previous appearances in 1607, 1531, and 1456. The 76-year interval suggested a highly elliptical orbit that brought the comet close to the Sun before flinging it back into the outer reaches of the solar system. Using my gravitational equations, I calculated the precise orbital elements of this comet, predicting that it would return in 1758. This prediction required extraordinary confidence in gravitational theory, since it extended mathematical analysis far beyond the realm of ordinary planetary observation into the poorly understood domain of cometary dynamics. The precession of equinoxes, a subtle shift in Earth's rotational axis that had been observed since ancient times, also yielded to gravitational analysis. The gravitational influence of the Sun and Moon on Earth's equatorial bulge causes our planet's axis to wobble slowly, completing one full cycle approximately every 26,000 years. This effect, which ancient astronomers had attributed to mysterious celestial influences, emerged naturally from the mathematics of universal gravitation. I demonstrated that Earth's shape itself reflected gravitational principles. The planet's rotation creates centrifugal forces that partially counteract gravitational attraction at the equator while leaving polar regions unaffected. This should make Earth slightly flattened at the poles and bulging at the equator, creating an oblate spheroid rather than a perfect sphere. This prediction contradicted measurements made by French expeditions, which suggested that Earth was elongated rather than flattened at the poles. The discrepancy created considerable controversy and was used by critics to challenge gravitational theory. Later, more accurate measurements confirmed my calculations, showing that Earth is indeed flattened by approximately 1 part in 300. The Principia also revealed the gravitational foundation underlying Kepler's laws of planetary motion. What Kepler had discovered through painstaking analysis of observational data emerged naturally from the mathematics of universal gravitation. Elliptical orbits, variable orbital speeds, and the relationship between orbital periods and distances all followed inevitably from inverse square attraction toward the Sun. This mathematical derivation of Kepler's laws provided powerful evidence that gravitational theory captured the true physical relationships governing celestial motion, instead of accepting these empirical patterns as mysterious facts about nature. I had shown why they must exist given the fundamental principles of motion and gravitation. The work also established the theoretical framework for understanding perturbations in planetary motion. The gravitational influence of each planet and all the others creates small but measurable deviations from simple elliptical orbits. These perturbations, invisible to casual observation but accessible to precise calculation, would later provide crucial tests of gravitational theory when improved astronomical instruments made their detection possible. Perhaps most remarkably, the Principia demonstrated that the same mathematical principles governing motion in our solar system must apply throughout the universe. Binary star systems, where two stars orbit around their common center of mass, follow the same gravitational laws as planetary systems. The clustering of stars into galaxies and the motion of galaxies themselves must ultimately reflect the same inverse square law of gravitational attraction. By the time I completed the Principia, I had established universal gravitation not as a speculative hypothesis, but as a mathematical fact confirmed by every available observation. The geometric demonstrations were rigorous, the predictions were precise, and the explanatory power extended from the smallest terrestrial phenomena to the largest celestial motions. The book represented a fundamental transformation in natural philosophy, establishing mathematics as the primary language for describing physical relationships and demonstrating that the universe operated according to comprehensible laws rather than mysterious forces. What had begun as a simple question about falling objects had evolved into a comprehensive understanding of the gravitational architecture that holds the cosmos together. The pendulum clock from the Royal Observatory ticks steadily beside my desk, its regular rhythm a testament to gravity's fundamental role in measuring time itself. This bronze instrument, crafted by the finest clockmakers of our age, demonstrates something profound about the force I discovered. Gravity's constancy allows us to divide time into equal portions, creating the foundation for precise navigation, astronomy, and all forms of temporal measurement. The relationship between gravity and timekeeping had not been obvious when I first began studying falling objects. Galileo had observed that pendulums of equal length swing with the same period regardless of the amplitude of their motion, but he did not fully appreciate the gravitational foundation underlying this remarkable consistency. A pendulum's period depends only on its length and the strength of gravitational acceleration, making pendulum clocks natural instruments for detecting variations in Earth's gravitational field. During my correspondence with the Royal Observatory, I predicted that pendulum clocks should run slightly slower near the equator than at higher latitudes. Earth's rotation creates centrifugal forces that partially counteract gravitational attraction at the equator, while the planet's oblate shape places equatorial regions farther from Earth's center. Both effects reduce the effective gravitational acceleration, causing pendulums to swing more slowly and clocks to lose time. The French expeditions to measure Earth's shape provided an opportunity to test this prediction. When astronomers carried precision pendulum clocks from Paris to equatorial regions of South America, they discovered exactly the effect I had calculated. Clocks that kept perfect time in Paris lost several minutes per day near the equator, confirming that gravitational acceleration varies systematically across Earth's surface. This variation in gravitational strength carries practical implications that extend far beyond clockmaking. Surveyors mapping large territories must account for gravitational differences when making precise measurements. Mining engineers can use gravitational variations to detect underground ore deposits or cavities. Artillery officers must consider how gravitational differences affect projectile trajectories when firing across great distances. But perhaps the most profound application of gravitational understanding lies in navigation and the determination of longitude at sea. For centuries, mariners had been able to determine their latitude by observing the sun's height at noon or the position of Polaris. But longitude remained a nearly insoluble problem. Without accurate timekeeping, sailors could not determine their east-west position with sufficient precision to avoid dangerous coastlines. The solution required chronometers that could maintain accurate time despite the motion, temperature variations, and humidity changes encountered during long sea voyages. My gravitational analysis of pendulum behavior provided the theoretical foundation for designing such instruments, though practical implementation required decades of additional engineering development. John Harrison's marine chronometers, which finally solved the longitude problem in the mid-18th century, applied gravitational principles in subtle but crucial ways. His compensating mechanisms accounted for how temperature changes affected the length of pendulum elements, while his escapement designs minimized the effects of ship motion on timekeeping accuracy. Every successful voyage using these instruments validated the practical importance of understanding gravitational principles. Tidal prediction represented another area where gravitational theory transformed practical knowledge. For millennia, mariners and coastal dwellers had observed the connection between tidal patterns and lunar motion without understanding the underlying mechanism. They developed empirical rules for predicting tides based on local experience, but these methods failed when applied to unfamiliar waters. My gravitational analysis revealed why tidal patterns vary so dramatically from place to place. The basic gravitational mechanism creates two tidal bulges that follow the moon's position, but local geography modifies this pattern in complex ways. Narrow channels amplify tidal ranges, while enclosed bays can create resonance effects that dramatically alter timing. Islands and underwater topography deflect tidal flows, creating local patterns that seem to bear little relationship to simple gravitational theory. Understanding these complexities required detailed analysis of how gravitational forces interact with fluid dynamics and coastal geography. I developed mathematical techniques for calculating tidal patterns in harbors, estuaries, and coastal waters of arbitrary shape. These calculations allowed for the first systematic tidal predictions, revolutionizing maritime commerce and naval operations. The Royal Navy immediately recognized the strategic value of accurate tidal predictions. Amphibious operations could be planned to take advantage of favorable tidal conditions, while knowledge of tidal patterns in enemy waters provided crucial intelligence for blockades and coastal attacks. The economic benefits were equally significant, as merchants could optimize shipping schedules to reduce voyage times and avoid dangerous conditions. Mining operations also benefited from gravitational understanding in unexpected ways. The precise measurement of gravitational variations across Earth's surface could reveal the presence of underground structures invisible to direct observation. Dense ore bodies create stronger gravitational fields in surrounding rock, while cavities or less dense materials create gravitational anomalies that sensitive instruments can detect.
This gravitational prospecting technique required extremely precise measurements, since the effects being detected were tiny compared to Earth's overall gravitational field.
But the practical rewards justified the effort, as mining companies could identify promising areas for exploration without expensive and time-consuming excavation. The application of gravitational principles to ballistics and artillery represented another practical triumph. Military engineers had long recognized that projectile trajectories curved downward under the influence of gravity, but they lacked the mathematical tools to calculate these trajectories with precision. My analysis of projectile motion provided the foundation for systematic artillery tables that dramatically improved accuracy. The key insight was that projectile motion could be analyzed as the combination of two independent motions, horizontal motion at constant velocity and vertical motion under gravitational acceleration. By calculating each component separately and combining the results, artillery officers could predict exactly where projectiles would land given the initial velocity and launch angle. These calculations became particularly important for siege warfare, where precision was essential for breaching fortifications without wasting expensive ammunition. Naval gunnery also benefited as ship's officers could account for the effects of gravity, air resistance, and ship motion when engaging targets at long range. But beyond these practical applications, gravitational theory revealed something far more profound about the nature of physical law. The same mathematical relationships that governed falling apples also determined the behavior of light passing through gravitational fields. Although I could not fully develop this insight with the mathematical tools available to me, I recognized that gravity might bend the path of light rays just as it curved the trajectories of material projectiles. This possibility suggested that gravity was not simply a force acting on matter, but a fundamental feature of space itself that affected all forms of motion and energy. The implications reach far beyond mechanical physics into the realm of optics and the nature of light. If gravitational fields could influence light, then astronomical observations made near massive objects might show systematic distortions that could be predicted and measured. My study of cometary behavior also revealed gravity's role in shaping the large-scale structure of the solar system. The gravitational influence of the major planets determined not only their own orbits, but also the paths of smaller bodies like asteroids and comets. This created a complex gravitational architecture that channeled some objects into stable orbits while ejecting others from the solar system entirely. The asteroid belt between Mars and Jupiter represented a particularly interesting case.
My calculations suggested that Jupiter's gravitational influence prevented the formation of a planet in this region,
instead maintaining a collection of smaller bodies in complex resonant orbits. This gravitational shepherding effect demonstrated how the largest planets shaped the overall structure of the solar system through their long-range gravitational influence. Even more remarkably, gravitational theory suggested that the solar system itself was embedded in a larger gravitational structure. If other stars possessed planetary systems, as seemed likely, then the gravitational interactions between stellar systems would create an even grander architecture on the scale of the galaxy. The same mathematical principles that govern planetary motion around the Sun would apply to stellar motion around the galactic center. This recognition that gravitational law operated on all scales, from the smallest terrestrial phenomena to the largest cosmic structures, provided a unifying vision of physical reality. The universe was not a collection of separate domains governed by different principles, but a single gravitational system operating according to the same mathematical relationships at every level of organization. As I worked through these applications and implications of gravitational theory, I began to appreciate the true scope of what I had discovered. This was not simply an explanation for why objects fall or why planets orbit the sun. This was the fundamental organizing principle of the physical universe, the invisible architecture that held everything together and determined the behavior of matter and energy on every scale, from the microscopic to the cosmic. My reflecting telescope stands in the corner of my study, its bronze construction gleaming in the candlelight. This instrument revealed Jupiter's moons following the same gravitational laws as earthly objects, providing the final proof that the force governing falling apples truly operates throughout the cosmos. Through its carefully ground mirrors, I witnessed the universe operating as a single comprehensible system bound together by mathematical law. The observations that confirmed my theoretical predictions came gradually, each one adding another piece to the vast puzzle of cosmic order. When I turned my telescope toward Jupiter and tracked the motion of its 4 largest moons over several months, I could calculate their orbital periods and distances with sufficient precision to test whether they obeyed the same inverse square law that governed planetary motion around the Sun. The mathematics worked perfectly. Io, Europa, Ganymede, and Callisto followed orbital patterns that matched my gravitational equations exactly. The closer moons orbited faster, the more distant ones slower, with the precise relationship between orbital period and distance that gravitational theory demanded. Here was direct observational proof that the same force responsible for terrestrial phenomena operated unchanged in the depths of space. But as I accumulated more observations and refined my calculations, I began to perceive something even more profound than the universality of gravitational law. The force that I had discovered was not simply one among many natural phenomena, but the fundamental organizing principle that determined the structure and behavior of the entire universe. Every star visible through my telescope exerted gravitational influence on every other star, creating an invisible web of attraction that bound the cosmos together. The patterns of stellar motion, the clustering of stars into groups, the very existence of the Milky Way itself, all of these large-scale structures reflected the operation of gravitational principles on scales almost beyond imagination. This recognition carried philosophical implications that went far beyond natural philosophy. If the entire universe operated according to mathematical laws that human reason could discover and understand, then there was a fundamental harmony between the structure of our minds and the structure of reality. The same logical principles that allowed us to prove geometric theorems also revealed the hidden order underlying all natural phenomena. The regularity I had discovered in gravitational relationships suggested that nature itself was rational in a deep sense. Objects did not fall because of arbitrary divine commands or mysterious sympathies, but because they obeyed mathematical relationships that could be expressed with the same precision as arithmetic calculations.
The universe was written in the language of mathematics, and human beings possessed the intellectual capacity to read and understand that language.
This mathematical comprehensibility of nature implied something remarkable about the relationship between mind and cosmos. We were not alien observers trying to penetrate an incomprehensible mystery, but rational beings whose capacity for mathematical reasoning reflected the mathematical structure of the reality we inhabited. Our ability to understand gravitational law was not an accident, but evidence of a fundamental correspondence between rational thought and natural order. The gravitational binding of matter into larger structures also revealed the creative power of this universal force. Gravity did not simply pull objects downward or hold planets in their orbits. It was the architect of cosmic organization, gathering diffuse matter into stars, collecting stars into galaxies, and shaping the large-scale structure of the entire universe. My calculations suggested that gravity played a crucial role in stellar formation. Regions of slightly higher density in the primordial distribution of matter would attract surrounding material through gravitational attraction, growing larger and denser over time. Eventually, these concentrations would become massive enough to ignite nuclear fires, transforming gravitational potential energy into the radiant energy that makes stars shine. This process implied that the stars themselves owed their existence to gravitational forces. Without gravity to collect and compress matter, the universe would consist of nothing but diffuse gas expanding into emptiness. Gravity provided the organizing principle that transformed chaos into the structured cosmos we observe, creating the conditions necessary for complexity, life, and rational thought. The realization that gravity shaped cosmic evolution on the largest scales filled me with a sense of awe that transcended mere scientific satisfaction. I had not simply discovered a force that explained planetary motion or terrestrial phenomena. I had uncovered the fundamental creative principle of the universe, the invisible hand that sculpted order from primordial chaos and made possible everything from stellar formation to the existence of rational beings capable of understanding natural law. Yet this cosmic perspective also imposed a humbling recognition of human limitations. If gravitational influence extended throughout the universe, operating on scales from the microscopic to the galactic, then there were aspects of natural law that lay far beyond our current capacity to observe or understand. The mathematical relationships I had discovered represented only the beginning of a vast program of cosmic comprehension. My telescope could reveal the moons of Jupiter and the phases of Venus, but it could not penetrate to the most distant stars or detect the subtle gravitational influences that shape the overall structure of the galaxy. The mathematical techniques I had developed could predict planetary positions and tidal patterns, but they could not fully capture the complexity of gravitational interactions in systems containing multiple massive bodies. These limitations suggested that natural philosophy would require the efforts of many generations to achieve anything approaching complete understanding. Each discovery would raise new questions, each answered question would reveal deeper mysteries. The gravitational force that I had identified was certainly fundamental, but it operated within a cosmic context that extended far beyond the reach of 17th century observation and calculation. The implications for human self-understanding were equally profound. We existed within a gravitationally bound system that stretched from the smallest particles to the largest cosmic structures. Every atom in our bodies had been forged in stellar cores through processes ultimately governed by gravitational forces. We were not separate from the cosmic order that gravity created and maintained, but integral parts of it. This recognition transformed how I understood the relationship between natural philosophy and human purpose. Scientific investigation was not merely an academic exercise or practical tool for improving technology. It was a form of cosmic self-awareness, a process by which the universe came to understand its own structure and operation through the rational activity of conscious beings. When I calculated the orbit of the moon or predicted the return of a comet, I was participating in something larger than individual intellectual achievement. I was contributing to the universe's growing comprehension of itself, helping to reveal the mathematical harmony that had been present since the beginning of time, but had remained hidden until rational beings evolved the capacity to perceive it. This perspective invested my scientific work with a significance that transcended personal satisfaction or professional recognition. Each mathematical relationship I discovered represented a small victory in the cosmic struggle between order and chaos, understanding and ignorance. The gravitational force that held the universe together also made possible the emergence of minds capable of comprehending that cosmic unity. The deeper I penetrated into gravitational theory, the more clearly I perceived this fundamental connection between cosmic order and rational understanding. The same mathematical principles that determine stellar motion also govern the processes that had led to the formation of planets capable of supporting life, and ultimately to the evolution of beings capable of discovering and appreciating mathematical law. As I worked late into the night with my telescope and calculations, I often felt myself in direct communion with the cosmic order that gravity maintained. The steady ticking of my pendulum clock marked time according to gravitational principles. The candlelight that illuminated my pages came from combustion processes ultimately powered by gravitational energy stored in stellar cores. Even my own thoughts and calculations depended on neural processes occurring within a brain whose very existence testified to the creative power of gravitational organization. This recognition of fundamental interconnectedness filled me with a sense of responsibility as well as wonder. If rational beings represented the universe's capacity for self-understanding, then the advancement of natural philosophy was not merely a human enterprise, but a cosmic imperative. Each generation of scholars inherited the obligation to extend and deepen the comprehension of natural law that previous generations had achieved. The gravitational force that I had discovered was both utterly impersonal, operating according to mathematical relationships that cared nothing for human desires or purposes, and intimately personal, creating the very conditions that made human existence and understanding possible. This paradox lay at the heart of the cosmic vision that emerged from my investigations of falling objects and planetary motion. A letter from Edmund Halley rests on my desk, its careful script expressing gratitude for showing him that the cosmos operates by comprehensible mathematical principles rather than divine caprice. His words capture something essential about what my discovery of universal gravitation accomplished. It transformed humanity's relationship with the natural world from superstitious bewilderment to rational understanding. When Halley first visited me in Cambridge to discuss orbital mechanics, he carried the intellectual burden that had weighed upon natural philosophers for millennia. How could mortal minds hope to penetrate the mysteries of cosmic order? What authority did human reason possess to pronounce upon the workings of celestial machinery that operated according to purposes beyond our comprehension? My gravitational calculations provided a startling answer to these ancient questions. The same rational faculties that allowed us to prove geometric theorems and solve arithmetic problems also gave us access to the fundamental laws governing cosmic phenomena. The universe was not an impenetrable mystery requiring supernatural revelation for its understanding, but a rational system whose deepest principles lay open to mathematical investigation. This transformation in humanity's relationship to nature extended far beyond the specific domain of astronomy and mechanics. If gravitational phenomena could be reduced to mathematical relationships discoverable by human reason, then perhaps all natural phenomena would eventually yield to similar analysis. The success of mathematical physics in explaining celestial motion suggested that mathematics might be the universal language of natural law. The philosophical implications rippled outward from my work into every area of human thought. If nature operated according to mathematical principles rather than arbitrary divine commands, then natural philosophy could achieve the same certainty and universality as mathematics itself. This possibility liberated human reason from dependence on ancient authorities and established observation and calculation as the ultimate arbiters of natural truth. The practical applications of gravitational understanding continued to multiply as subsequent generations of natural philosophers built upon the foundation I had established. Navigation became a precise science rather than a collection of empirical rules. Tidal prediction allowed coastal communities to plan their activities with unprecedented accuracy. Artillery officers could calculate projectile trajectories with mathematical precision. But beyond these immediate, practical benefits, gravitational theory established a new model for how human beings could relate to the natural world. Instead of seeing ourselves as helpless subjects of incomprehensible forces, we could understand ourselves as rational beings capable of discovering and applying the mathematical laws that governed all natural phenomena. This shift in perspective influenced fields far removed from physics and astronomy. If the motion of planets could be calculated with mathematical precision, why not the circulation of blood through the human body, or the patterns of trade in commercial markets, or the principles underlying political organization? My demonstration that mathematical reasoning could penetrate cosmic mysteries encouraged scholars in every field to see quantitative relationships underlying qualitative observations. The confidence that mathematical analysis could reveal hidden order in apparent chaos became one of the defining characteristics of the age that followed my work. Natural philosophers no longer accepted that certain phenomena were simply too complex or mysterious for human understanding. Instead, they assumed that patient observation and careful calculation would eventually reveal the mathematical principles underlying any natural process. This optimistic rationalism carried risks as well as benefits. Some of my successors became overly confident in the power of mathematical reasoning, assuming that all aspects of reality could be reduced to mechanical calculations. They forgot my own recognition that gravitational theory, however successful, represented only the beginning of cosmic comprehension, rather than its completion. The mathematical techniques I had developed for analyzing gravitational phenomena proved applicable to problems I had never anticipated. The calculus of variations, differential equations, and analytical geometry became standard tools for investigating natural phenomena across the entire range of physical science. Each new application confirmed the fundamental insight that nature spoke in mathematical language. Yet, as gravitational theory matured and its applications multiplied, I became increasingly aware of the profound questions that my work had raised without answering. How did gravitational attraction actually operate across empty space? What was the relationship between mathematical description and physical reality? Why did the universe conform to mathematical principles that human minds could discover and understand? These questions pointed toward mysteries that lay beyond the reach of 17th century natural philosophy. I had demonstrated that gravitational phenomena followed precise mathematical laws, but I could not explain why such laws existed or what ultimate reality they reflected. The success of mathematical physics deepened rather than resolved the fundamental puzzle of cosmic order. My correspondents often pressed me to speculate about the metaphysical foundations of gravitational theory. What was the ultimate nature of the force I had discovered? How did matter acquire the capacity to attract other matter across empty space? What purpose did gravitational organization serve in the cosmic scheme?
I learned to respond to such questions with careful restraint.
Mathematics had given me access to the precise relationships governing gravitational phenomena, but it did not reveal the ultimate nature of the reality underlying those relationships. I could describe what gravity did with extraordinary precision, but I could not say what gravity was in any final sense. This intellectual humility became one of my most important contributions to natural philosophy. By demonstrating the power of mathematical description while acknowledging its limitations, I helped establish a new model of scientific understanding that was both confident in its achievements and modest about its ultimate reach. The letters I received from younger scholars often reflected a transformed relationship to natural investigation. They approached their studies with an optimism about human rational capacity that previous generations could never have imagined, yet also with a disciplined focus on observation and calculation that kept speculation grounded in empirical evidence. Halley's work on cometary prediction exemplified this new approach to natural philosophy. He applied my gravitational calculations to predict the return of the comet that now bears his name, demonstrating that mathematical physics could make precise prophecies about celestial events decades in advance. When the comet returned exactly as predicted in 1758, 16 years after Halley's death, it provided dramatic confirmation that human reason had indeed penetrated cosmic mysteries that had puzzled humanity throughout its history. The success of such predictions established a new standard for natural knowledge. Theories were not simply required to explain known phenomena, but to make precise predictions about future observations. This predictive criterion separated genuine scientific understanding from mere philosophical speculation, providing a reliable method for distinguishing between competing explanations of natural phenomena. As I reflect on the decades that have passed since I first questioned why objects fall toward Earth, I am struck by how completely this simple investigation transformed human understanding of our place in the cosmos. What began as curiosity about falling apples evolved into recognition that we inhabit a universe governed by comprehensible mathematical laws rather than incomprehensible mystery. The gravitational force that binds the cosmos together also created the conditions that made human reason possible. The same mathematical principles that determine stellar formation and planetary motion also govern the processes that led to the emergence of minds capable of discovering and appreciating cosmic order. We are not accidental observers of natural law, but integral participants in the universe's capacity for self-understanding. This recognition invests scientific investigation with a significance that transcends practical application or intellectual satisfaction. When we discover mathematical relationships underlying natural phenomena, we participate in the cosmic process by which order emerges from chaos and understanding emerges from ignorance. Each scientific advance represents a small victory in the universe's long struggle towards self-comprehension. The work that began in my mother's orchard during the plague years has become part of humanity's permanent intellectual heritage. Future generations will build upon these foundations, extending mathematical understanding into realms I cannot imagine. They will face new mysteries and develop new techniques, but they will do so with confidence that rational investigation can penetrate the deepest secrets of natural order. The apple that fell beside my window so many years ago spoke in a language that took decades to learn. It told of forces that bind the cosmos together and laws that govern motion from the smallest to the largest scales. Most importantly, it revealed that this cosmic language is written in characters that human reason can decipher, making us partners in the universe's ongoing project of self-discovery. Before that moment of questioning why things fall, we saw ourselves as strangers in an incomprehensible cosmos. After discovering the mathematical harmony underlying gravitational phenomena, we know ourselves to be rational beings inhabiting a rational universe, capable of understanding the very forces that created the conditions for our existence. That transformation in human self-understanding may be the most profound legacy of the investigation that began with a simple question about falling objects.